Alfred, and welcome to the continuation of our tutorial on how optical brighteners work and how we use those in the paper industry. Now this particular video is going to be on actually both the TAPI and the ISO discussion. So this introductory piece we have right here, once you've watched it once, you can skip that section on the other video, but if you'd like to watch it again, obviously that choice is yours. And the reason is because this information is the same for both TAPI and ISO, so we're just putting it on both just in case you don't watch one, you'll at least get it on the other. Just as a quick overview, the purpose of an OBA, an optical brightening agent, is to make white paper brighter or whiter, whichever measurement you make in brightness or whiteness. The goal is to do that, and they accomplish that by, again, absorbing energy in the UV region of the spectrum and emitting that energy over here in the blue region of the spectrum where brightness is measured, but also if you do a whiteness measurement, papers, those formulas are biased to reward blue-white paper. So you still get that bump in whiteness because of that. So it's important that we know how to manage and how to control the dosage of the optical brightener in our processes so that we can manage that properly. One of the problems that you'll get into, and again, when we talk more specifically in the color presentation in relationship to optical brighteners, we'll dive a little bit deeper into this, but as you dose an optical brightener, the law of diminishing returns kicks in. So I could put in a little bit and get a nice bump. I can put a little bit more and I'll get a bump, but that bump it'll start to decrease its value. So I might put in X and I get X in return. I might put in X plus, but I get X plus a little bit less in, and the more I put in, the less movement I get up here on the peak side of things, until at some point actually you oversaturate the system with an optical brightener, and when you do that, then the actual optical brightener begins to combine back together again. And as I mentioned earlier, the optical brightener is a little bit on the yellow side, but anyway, you get this greening effect. So you actually shift the color of the sample towards the green, and so you were starting to overdose your sample at that point. So it is critically important in optimizing your operations that you learn what is the proper dosage of your optical brightener, and that can vary depending upon your fiber source and the other things that are going in to make up your paper. It's important we understand what tools we have for evaluating that, and that's really where we come in with the brightness measurement as the primary tool that most people will use when they're dosing and measuring the effect of an optical brightener. When we talked about brightness, we talked about its original setup was back in the 1930s by the Institute of Paper Chemistry and General Electric at the time, and that unit was set up to evaluate the bleaching process, which we have right here. When ISO developed their brightness method, likewise, it was to monitor the bleaching process, and really we were dealing with, at the time, for the most part, naturally occurring colorants in there that we were removing in this process. Once we introduced the optical brightener into the process, we then took that instrument that was developed to do either TAPI or ISO, and we applied that instrument to that process, even though now it's measuring something that the original instruments weren't designed to do. Fortunately, because we're still talking about the blue region of the spectrum, a TAPI instrument or an ISO instrument still does a very effective job of managing that. So when we measure brightness in the industry today, that is done under what's called, I'll write this up here, UV or ultraviolet, and you'll often see a small IN for included. So it's UV included. So what that means is that if there is ultraviolet energy in the light source of that instrument, that ultraviolet energy is included in the measurement. So it's going to illuminate the sample, and if there's an optical brightener there and you have UV content in that light source, then that optical brightener is going to fluoresce, and that is going to be included in that brightness or whiteness number. Okay, so it is measured UV included. So to determine the impact of the optical brightener, you have to make a second measurement. And you'll hear the phrase UV excluded, and you'll see an EX with that. And UV excluded means is that what we've done is that you've got a light source whether it's tappy or ISO, you have a light source, and you've got a UV cutoff filter. So we have very specific filters, glass filters that we use that are manufactured in such a way that they cut off certain levels of energy. More often than not, it's a 420 nanometer filter, and what that does is that cuts off light here in the blue region of the spectrum, but its primary purpose is to make sure there is no UV energy that's going to illuminate the sample, so that if there's an optical brightener present there, and now I'm illuminating with this light that has the filter over that incident beam, now that UV energy cannot get to the sample, so that sample can't fluoresce. So it's in a UV excluded environment. And so what happens then is that you will take UV included measurement, UV included, and you will subtract from that the UV excluded value, and that will give you this value called fluorescent component. And it's UV included minus UV excluded, and you get this value called fluorescent component, and that is the effect of the optical brightener. So the optical brightener is increasing my brightness from whatever the UV excluded number is to whatever the UV included number is. So let's just say, for the sake of ease, this was 85 for UV included, and UV excluded was 80. So it would be 85 minus 80, and my fluorescent component was 5. So it means that I'm getting a boost in brightness of 5 points due to the presence of the optical brightener. Okay, so whether we're doing tappy brightness or ISO brightness, both methods call for a UV included measurement and then a UV excluded measurement, and the difference between those two are what we call the fluorescent component. Okay, and so it's just UV included minus UVX equals fluorescent component. Very simple. If there are no optical brighteners in the sheet at all, so there's been no dosage of an optical brightener, UV included, UV excluded will agree, and so the fluorescent component value would be equal to 0. All right, so now what we're going to do is we're going to take and we're going to break that down for tappy and ISO. Now the rest of this video we're going to talk more specifically about how ISO handles the measurement of fluorescence. Okay, so I've got two different instruments here. This is our Test Plus ISO brightness instrument, so it does ISO brightness and fluorescence. This is our Color Touch X instrument, and this one is a more advanced instrument. It's a spectrophotometer. There's a lot of different measurements, but the one additional thing it does, just like this one, it measures ISO brightness and it measures fluorescent component. So it has capability of doing more than just brightness. But we have them both in here because of the additional information that you'll get from the Color Touch X, which will highlight some of this information over here, but we'll also come back to this when we talk more specifically about color. Okay, so where we left off last is that we have UV included and UV excluded measurements. Okay, so back in the 1950s when ISO was developing these instruments, like we said, we weren't really worried about optical brighteners at the time. Okay, so the amount of UV energy in the light source was really irrelevant for the application at the time. But once we started introducing optical brighteners into the paper itself, then we had to come up with a way of measuring that, measuring the effectiveness of that. So we did that through this method. But what's important to also understand is the amount of ultraviolet energy that is in your light source, because that will directly impact how much fluorescing you get if you have an optical brightener present. So initially, with some of the instruments, they used a QTH lamp, a quartz tungsten halogen lamp. And a quartz tungsten halogen lamp is what you would find in an old Technonine TB-1 instrument or a Micro TB1C. We also find that light source in one of the Test Plus instruments. That is going to be fairly similar to what maybe a 60-watt light bulb, a tungsten lamp, would be. And that's going to have, if you're able to look at this, and so you'd have a lot of more red energy, some green energy, less blue energy, and you'd come down looking like that. Okay, so that light source is a very orange or yellow colored light source. All right, think about it though. Indoor lighting environment, especially back in the 1950s, 60s, and 70s even, was mostly made up of tungsten lamp. And even in your home today, you may still have a lot of tungsten lamps in that area. Excuse me, in your home where you are viewing things with. So it's still a very relevant light source today. like we mentioned in the previous video, where we're introducing the optical brighteners and how we measure them, with most paper being viewed indoors, it is a low UV light environment. So not a lot of ultraviolet energy. So the original setup of these guys for measuring the effect of an optical brightness was actually pretty accurate to what the indoor viewing environment would be. So you would basically illuminate it. UV included would be this QTH energy. Okay, so you've got this energy over here in the UV region of the spectrum. So you can see it's a low level of energy. You make that measurement. You put that cutoff filter in, get the UV excluded reading, and you get your fluorescent component. It was really simple the way that did that. So if I step around here and I load, let's say, this sample onto this instrument. Okay, so the sample is loaded, and now the instrument is in the fluorescent mode. So what we're going to do is we're going to make the measurement. So I will touch test, and the first thing it does is it measures the UV included value. Then it readjusts the light source to where now we're excluding the UV energy, and we get the UV excluded value. So then it's just a simple math of UV included minus UV excluded to give us this value here, which is the effect of the optical brightener. So in this case, we're seeing that we get an increase in brightness of 10.9 units due to the presence of the optical brightener and the ultraviolet energy. Okay, so you can see even in this case, the effect of the optical brightener can be quite substantial in achieving the brightness levels that you need to for your application. Again, if I had a sample on there that contained no optical brighteners, my reading would basically be 0. Sometimes you might see 0.1 or negative 0.1 just because the instrument has to reconfigure itself and may not come in perfect every time, but that's certainly acceptable. And even in some pulps, there are naturally occurring fluorophores that will be there. And even though you may not have added an optical brightener, you might see a number of 0.3, 0.4, and it's probably due to some natural fluorescing going on with that, even though you haven't added it to it. So anyway, that was kind of where the industry was going with things. And then we introduced this concept of a xenon flash lamp. Now, a xenon flash lamp is a high-intensity light source similar to what you might have on your camera. Okay, so a very bright, intense light source. That light source also is very high in ultraviolet energy. So, again, this is an approximation here, but if you think of this being a QTH light source, a xenon flash lamp light source might have energy more like that. So you're going from an energy differential from here to here. And that would be somewhat consistent with outdoor daylight, so it's a very rich light source. So those were on some instruments, and you could control how much UV energy you could allow into your sphere of the instrument by just adjusting a knob. And so obviously the higher brightness you get, the more value you get from your paper. So it wasn't an uncommon practice to see instruments dialed up with the UV filter all the way out, letting all of the UV energy into the sphere, and basically over-exciting the optical brighteners and getting numbers that were, 120 and higher on brightness. And it was not going to be representative of the viewing environment at all because, again, most viewing environments were low energy. So the ISO committee went back to work on how do we manage this. And so they standardized on a new light source, which they called source C. And source C was going to represent this typical viewing environment. Turns out source C is a bit more UV energy than the QTH lamp was, but it was quite a bit less than where the D65 was. And so at that point they implemented a procedure where you would use a 395 trim filter, and that trim filter would be adjusted so that it was blocking a certain amount of ultraviolet energy from the xenon flash lamp so that you could get a consistent UV content level from your light source to be able to measure properly with that. So ISO then defined this source C for measuring ISO brightness. So the UV included for ISO brightness uses this value called source C, which is a definition of the UV energy that is going to be allowed into the sphere to make a measurement. When they did that as well, they also knew that people wanted a higher UV source level for doing a whiteness measurement. And you'll need to watch the whiteness video to understand a little bit more detail of that. But they wanted to be able to get a higher level of UV in there. A lot of that went around the ability to control the addition better, because if you expand your scale, the thought was if I expand my scale of control, then I have better ability to really fine-tune things. So the D65 source was developed, and that is a very UV-rich light source, not dissimilar to what this green line represents here. That is a flash lamp, a xenon flash lamp. So the 395 filter then is used to trim that energy to be able to get the D65 level. So today in the ISO world, you've got C source, you've got D65 source, and you have UV excluded. Okay. Now we're here with the Color Touch X, and we're going to do some measurements with it. So I have a couple different presentations set up here, and the first one I'm going to choose is this one I just called fluorescence. Now this presentation is designed to measure both under source C and UV excluded, again giving us fluorescent component values. Okay, so I will load my sample, which contains optical brightener, and I will choose measure. The instrument will now configure itself to measure under source C, so adjusting the filters to trim the ultraviolet energy to match source C. Once it completes that test, then it will do the UV excluded test. Now this presentation also does color. We're not going to look at that right now. We'll focus just on brightness right now. So brightness under UV included is 90.19. Next column is UV excluded, and it's 84.32. The third column is the component value. So the delta brightness is 5.87, or roughly 6. So the fluorescence boost we're getting to our brightness is 6 points with that. Now I can come across the bottom here, and I can choose the spectral curve. And with this you can see kind of the full picture, but focus on this region between here and here, that 4 to 500 region, the blue region of the spectrum. I'll actually expand that for us to see that a little bit better. And you can see that increase in energy from the line below, which is UV excluded, to the line above, which is the UV included, and that is the impact of the optical brightener. So if I back out of that, you'll notice is on the UV excluded line, a straight line going across. The standard calls that at 420 nanometers, where the UV cutoff filter is that you take whatever that data point is and you just extrapolate that out through the rest of the spectrum. So that's why you have that odd line going right there. Okay, so that's that sample under source C. So I can close that presentation out, and I'm going to open up this second presentation, which I set up to be just like the previous one, but now instead of measuring under source C, it's going to measure under source D65. So you can see we've got D65 and UV excluded. So now I'll hit measure. Notice I didn't move the sample, didn't change the sample. It's the same exact sample measured at the same location. The only difference is now we're exciting those fluorescing agents, the optical brighteners, with a light source which is UV rich, D65. So we'll see an elevation in our numbers because of that. So now the UV included, or D65 value, is 96.5. The UV excluded stays the same, and our component value now is 12.19 or 12.2, let's say. So now we're getting an increase in brightness of 12.2 units because of the presence of the optical brightener and the UV rich conditions. So it's more than twice the amount of increase that we got under source C. So you can see the impact of the optical brightener, but also the impact of the UV energy that's in your illuminating source. I'll choose the spectral curve, and again you can see this area here, and you can see a greater difference between the UV excluded data and the UV included data. So there's a lot that goes on when we're talking about the measurement of optical brighteners in the ISO world. What's important to know is that you've got to specify, am I measuring under source C or source D65, because obviously you can get quite a bit of difference between the two. So, like always, if you have questions or if there's anything we can do to assist you, don't hesitate to call us, as this is what we enjoy doing. And our goal at the end of the day is that we can help you make a better paper.